This is a lecture about covalent bonding, and you may remember that covalent bonds are bonds where the two bonding atoms share their valence electrons rather than completely transferring valence electrons as is done in an ionic bond. And so a covalent bond is an electrostatic attraction, just like all chemical bonds are. But the electrostatic attraction is between the electrons of one atom and protons of the other. And the electrostatic attraction of involved in an ionic bond is stronger because it's of a fully charged anion with a fully charged cation. But all bonds, again, are electrostatic attractions. So there's some vocabulary you should be familiar with, especially if you're drawing a Lewis structure for a covalent bond. As we've talked about before, with the Lewis structure, dots represent the valence electrons. So if you have a covalent compound, you're going to have bonding pairs of valence electrons, and those are the ones that are shared between the two atoms that are bonded. And then you're going to have non-bonding pairs of electrons, also called lone pairs, that just exist solely on one atom and belong to one specific atom. So you may know that covalent bonds can be single bonds, double bonds, or triple bonds. If it is a single bond, that means that one pair of electrons are shared between two atoms. So if I were to draw a simpler version of water, H2O, this is a single covalent bond and it's made up of two electrons. Now, a double bond, such as we have in molecular oxygen, would have 4 shared electrons. Okay, so we look at the different versions of the Lewis dot structure for a double bond, or for oxygen specifically. And you can see, if I asked you how many bonding pairs of electrons and how many non-bonding pairs are there in this structure, hopefully you would say, all right, there are 2 bonds. All right, so commit these prefixes to memory. And just to kind of show you a flow chart of the rules, you're going to name the first element, will be the less electronegative one. It gets a prefix unless, this is huge, so pay attention down here, unless there is only one atom of this element. If there's only one, then the prefix is left out. But that's the only exception. And then the second element will have a prefix, always, even if there's only one of them. And you also have to remember to give the second element, the last element, an IDE ending, just like we did in ionic compounds. So let's practice some of them. All right. Nitrogen, triiodide. Now, the whole rule I told you about naming the less electronegative first, honestly, 99% of the time, if you're given the formula, go ahead and just name the one that's shown first in the formula first, okay? And then just don't worry about it. So remember the exception that if there's only one of the first element, you leave off a prefix. So you would not say mononitrogen, okay? So it's just nitrogen triiodide. Here's another one. Again, the first element, there's only one of them, so you do not say mono, okay? It's just phosphorus. The prefix for 5 is pentachloride. Remember the IDE on the end. Here's one that's a little bit more complex. Tetra is a prefix for 4, phosphorus. Now the first one, just like an ionic naming, is the exact name of the element. Don't put any suffix or anything there. Deca is the prefix for 10, and then sulfide. Alrighty, so that's pretty easy, and you want to challenge yourself now, since a covalent naming is so easy, by getting a practice worksheet out that has a mixture of ionic and covalent, and go through and see if you can sort all those out. I just want to introduce you to a few pieces of information about organic compounds. Organic compounds are any compound that contain carbon. Okay. Chemistry is divided two big branches into organic chemistry, so that's compounds containing carbon, and inorganic chemistry. I think that division started originally when organic chemistry was the chemistry of living things. I think that's how it originally started. That's not the case now. It's basically anything that has carbon. Okay, so most of the organic compounds are what we call hydrocarbons they're made of carbon and hydrogen, but also it's very frequent to see oxygen, nitrogen, phosphorus, and sulfur. Carbon, since it's in group 4A, doesn't really prefer to make ions, and so the vast majority of bonds carbon makes are covalent bonds. And so organic chemists really don't work much with ionic bonds. Again, because carbon is in group 4A, it has 4 valence electrons, and therefore it tends to make 4 bonds so that it can get its octet. So you will typically see carbon with 4 bonds. There are a couple of real simple functional groups or names in organic chemistry that I'd like to introduce you to, and they are the following. If an organic compound is made up of only carbon and hydrogen, okay, so only carbon and hydrogen and all single bonds, no double bonds or no triple bonds, okay, they are called alkanes. So I want you to remember that. So propane, isobutane, and hexcyclohexane, okay? So alkanes end in ane. If an organic molecule is made up, again, only of carbon and hydrogen, but if it has a double bond instead of all single bonds, it is an alkene, okay? And the ending when you named it would be -ene. And here we go. If it's made up of carbon and hydrogens and it has a triple bond, it is called an alkyne. Okay, so they would end ethyne. So compare these two, ethene, ethyne, and there is an ethane also. So ethane would have all single bonds between the carbon and hydrogen. Ethene has a double bond, ethyne has a triple bond. So I would like you to know what an alkane is, what an alkene is, and what an alkyne is. And then the other common one is a carboxylic acid. You will see that quite a bit. You'll see that in Gen Chem also. And that's carbon, double bond oxygen, and then an OH also off the same carbon. And they function as weak acids, which we'll learn later on in Gen Chem. All right, this just gives you the different ways to represent organic molecules. So the condensed formula, which we're most familiar with, using single lines to represent single bonds, double lines to represent double, and 3 to represent triple. And these are the space filling models that are probably a more realistic demonstration of the molecules. And that is it for covalent bonding.